This is the second video in the collisions topic. In this video, we'll take a look at how we can apply Newton's laws to systems with more than one part, and there'll also be a very brief recap on linear momentum. So by now, you are all hopefully very familiar with Newton's laws. Hopefully you've done enough questions that you are close to being thoroughly sick of Newton's laws. We know that Newton's laws apply only when we can assume an object is particle-like. What we want to look at here in this video is how Newton's second law can be applied to a system of particles. So Newton's second law we're probably most familiar with in this form, which is F equals ma. But we also know we have the momentum, P equals mv, and so we can also write Newton's second law as F net is equal to the change in momentum over time. In the previous video, we saw that we could describe the behaviour of an odd-shaped object, such as a tennis racket, or a system of particles, using the centre of mass of that system. And we know that the centre of mass is governed by Newton's laws, and that is probably the most important thing that you need to remember from this video. So when we're dealing with the centre of mass, we just have to take care that we use the right mass and the right acceleration, or the right momentum, in the equations. So in this case, the net force on a system is equal to the total system mass times the acceleration of the centre of mass. And in a similar vein, the total momentum of the system is equal to the total mass of the system multiplied by the velocity of the centre of mass. So nothing has really changed for us, which is very nice. When we describe the motion of a system using the centre of mass behaves like a particle-like object, and we can directly apply Newton's laws. In these equations, we're still dealing with vectors, so we can also write the force and momentum on the individual x, y, and z components. Let's have a look at a quick example. In this example, we're given forces acting on 4 different particles, and we're asked to find the acceleration of the system as a whole. So running through our method, we've already been given a diagram, the coordinate system, and a list of our information. Because it is a system with several objects, we want to find the acceleration of the centre of mass. We know that by Newton's second law, it's equal to the net force divided by the system mass, and so we only need to find those 2 variables. We don't have enough information to find the system mass, so really all we're looking for now is the net force on the system. By now, we're hopefully pros at that, so I won't go into it in detail. We would find each of the x and y components of each of our 4 forces, and we would sum them together. And we would find that F net is equal to 11.2i plus 25.4j. Calculating the magnitude and direction using Pythagoras and the tan trig identity, we get that force in magnitude and direction is equal to 27.8 newtons east 66 degrees north. So we have our net force, and to find the acceleration we then just divide through by our system mass, which is easy peasy. And that's really all there is to it. So the only thing we need to remember when working with systems of particles or odd-shaped particles is that Newton's laws of motion and our force analysis applies to the acceleration and the velocity of the centre of mass of the system.